Welcome back to my today's session of electromagnetic field. Today I am going to tell about the definition and terminology on magnetostatics. Myself Dr. Sayanti Chatterjee. I am the Associate Professor of Department of Electrical and Electronics Engineering in IARE, Hyderabad. So, before starting my today's topic, first we will discuss about the magnetostatics. What do you mean by the magnetostatics? Magnetostatics, unlike the electrostatics, it depends on the magnet. So, if we go for the definition, magnetostatic is nothing but the study of the magnetic field developed by the constant current through the coil or due to permanent magnet. So magnetostatics is always deals with the constant current. The current should be DC, and it is also due to the permanent magnet. According to the field theory, the field is basically three types. One is called the electrostatic field, which is only depends on the electrical poles, and one is the magnetostatics field, which is depends on the constant current. Another third one is the electromagnetic field. Electromagnetic field means this field works for the electric field as well as the magnetic field. So magnetic field is the combination of the constant current and the permanent magnet. As we know, if there is a solenoid if we keep a solenoid on any iron body like this, and we connect any source with it, the constant current, the DC current will flow and it will create a electromagnet, north pole and south pole. So for this also there will be a field, and this field is a magnetic field. So magnetostatics is a one part of study of magnetic field. Next question, what is the difference between the magnetostatics and electrostatics? As there are two dominating field, magnetic field and electric field, so they are not same. So what is the difference? So first if we discuss on it, as the name defined, the magnetostatics field or magnetostatics is due to the magnetic field when the constant current will flow. On the other side, electrostatics is about the electric field. Now, what is the force on charge? In the case of the electrostatic field, the force on charge is Q into E. Q is the amount of the charge of the field, and what is E? E is the electric field intensity. On the other side, it is the A is equal to Q V cross V. Q V cross V. So this is the force on a charge due to the magnetic field. What is the field intensity? As we told here, field intensity is E and the unit is volt per meter. Field intensity in the case of the magnetic field is H, and it is ampere per meter. So, and what is B? Here B is the magnetic flux density. What is B? V is nothing but the velocity of charge, because we know velocity of the charge means when the electrons flow in any conductor, in the opposite side current will flow. So we will take the velocity of charge. Third point is the flux density. Flux density D is equal to, and its unit is Coulomb per meter square. What is D? Number of electric flux in the cross-sectional area. And according to the Gauss law, number of electrical flux is equal to electrical charge enclosed. So we can write D is equal to Q by S. So Coulomb per meter square. On the other hand, the flux density in the magnetic field is B, and we can write it phi by T. Phi by S. What is phi? Phi is the number of magnetic flux. So what is the unit? The unit is either Weber per meter square, or we can call it by Tesla. What is the third point? Third point is the material relationship. We know D by E is equal to permittivity of the medium. What is permittivity? The amount, the property of any medium where it can store the electrical energy. In the opposite side, B by H is equal to mu. What is mu? Mu is the permeability of the medium. So, in the case of the static charge, the energy is stored in the form in the capacitor. The energy storage property in the capacitor. In the case of the magnetostatics, the energy stored in the inductor. So, what is the source? As we discussed previously, the source is due to the static charge, and this is the source due to the permanent magnet or steady current. So, these are the difference between the electric field and the magnetic field. Question number 3. Name the laws used in the magnetostatics. So, what are the main laws which dominate the magnetic field or magnetostatics property? The behavior of constant magnetic field is studied by two laws. They are, first one is the Biosubards Law, and second one is the Ampere circuital law. So these two laws are basically the main background of the magnetostatics or the magnetic field. The Biosubards Law tells about the field density and relation of field intensity. Ampere circuital law is field intensity and current. So these two laws are the basics of the magnetostatics. So while we are discussing about the magnetostatics, the first thing which will come into our mind, what is magnetic field? So first, before telling about the magnetic field, we will give a short demo of the electric field. What is the meaning of electric field? The amount of force required to bring one unit charge from infinity to any area. So, we know according to the Coulomb's law, we can write the electric field intensity is equal to Q by 4 pi r squared AR. AR is the unit vector, and AR gives the direction of the electric field intensity. Similarly, magnetic field is also a vector field. This is the first important term. So, this is a vector field. The magnetic field is a vector field that describes the magnetic influence on the moving electric charges or electric currents or magnetic material. So this is also a magnetic field which gives some influence on the electric charges, electric currents and any type of magnetic material. A moving charge in a magnetic field experiences a force perpendicular to its velocity to the magnetic field. As we discussed earlier, when there is a magnetic field, it will experience some force, and F is equal to Q V cross B. What is the meaning? Its own velocity V and the magnetic field intensity B. And what is the direct, as this is a cross product? So from here you can understand that the force is directly is in the 90 degree perpendicular to its own velocity. The formation of the field is always from north pole to south pole. Third important property of the magnetic field is the formation of the field. The field is always formed from the north pole to south pole. The right hand the direction of the magnetic flux or like the magnetic field is always comes from the right hand thumb rule. What is right hand thumb rule? If we keep the first finger, middle finger and thumb in perpendicular to each other, the if the thumb gives the direction of the velocity of the charge or magnetic pole and the first finger gives the direction of B, that is the magnetic field or magnetic flux density, the direction of the force will be according to the middle finger. So this is the right hand rule of the magnetic flux. So as I told that it is a north pole and south pole, and you can see the field lines are from north pole to south pole. Always it will originate from the north pole and always terminate in the south pole. So this is the magnetic field. So after magnetic field, the another topic which will comes in our mind is the magnetic flux density. What is the meaning of the magnetic flux density? So magnetic flux density is the magnetic flux per unit area. We can write magnetic flux phi by A. Now, magnetic flux density is also defined as the differential change in the flux by differential change in the area. So, V is equal to d phi by ds. The differential change in the flux by the differential change in the cross-sectional area. So, what is d phi? D phi is nothing but the V into ds. So, what is phi? Phi is the integration of V into ds. The unity of the flux density is Weber per meter square and we call it also as the Tesla. So, magnetic flux density is one of the important thing in the magnetostatic study. There are two definitions. First definition is the magnetic flux density is the ratio of the magnetic flux per cross-sectional area, or we can tell that the differential change in the magnetic flux to the differential change in the the cross-sectional area. Next important definition of this chapter is the magnetic field intensity. So again we will discuss from electric field intensity. E is equal to, according to the electric field intensity, E is equal to Q by 4 pi r square AR. The force required to bring one unit positive charge from one point to another point. Similarly, in the case of the magnetic field intensity, we can tell the force required to bring one unit positive north pole from one point to another point. So, the definition wise it is same, only change in the case of the electrostatic field to bring one unit positive charge. In case of the magnetic field, to bring one unit north pole. So, what is the physics behind it? The degree to which magnetic field can magnetize a substance or the capability of external magnetic field to magnetize the substance is called the magnetic intensity. So, what is magnetic intensity? The degree to which a magnetic field can magnetize a substance and or the capability of any material to magnetize the substance is called the magnetic intensity. So, magnetic intensity can be written as the force experienced by the coil when some current is passed through the magnetic intensity. H is equal to Ni by L. What is N? N is equal to number of turns of the coil. What is I? I is the current passing through the coil. Through the coil. And what is L? The length of the conductor. So this is the definition of the magnetic field intensity. So what is the unit? The number of turns unit is turn, current unit is ampere, so we can write it ampere turn meter, and the magnetic field intensity is always denoted by H. So next is the define the magnetic susceptibility. So another term of this is the electromagnetism is the magnetic susceptibility. It is written by the Xi. So what is magnetic susceptibility? Magnetic susceptibility is a measure of how much a material will become magnetized when we will apply the field. See, we have one iron bar. In the normal condition, iron bar, the atoms are in the random nature. Now, if we give any source to it, it will align themselves in the direction of North Pole and South Pole. The magnetic susceptibility will tell how much the material will, how many atoms will magnetize or assign themselves in the direction of the North Pole and South Pole. It is the ratio of the magnetization M to the applied magnetic field H. So it is also, we can tell, this is the ratio of the magnetization M. What is the meaning of the magnetization? Magnetic moment per unit volume. So magnetization to the applied field, or we can write it by K is equal to I by H. Total flux density B will be changed due to the magnetization, and it will be B equals to mu naught I H plus I. So what if we put the value, we can, what is I? I is nothing but the magnetic moment. So if we put the value, we will get mu naught is equal to mu r is equal to 1 plus K, and this is known as the Xi, or the magnetic susceptibility of the medium. So magnetic susceptibility gives the degree at which how much a material will become magnetized. So after this important thing, the next term comes the permeability of a core. So what is the meaning of the permeability of a core? So if we discussed about the permeability of the core, we can tell permeability is the inherent property of the core which helps in sustaining the flux in the core. So permeability is the inherent property of a core which helps if there is any flux. So it helps in sustaining the flux in the core. So if we are thinking about the iron or any paramagnetic material, it has very high permeability. And what is the meaning of the very high permeability? Very high permeability means it will helps the more flux to stay in the core, and that's why the transformer core is always made of the silicon steel or the steel product, iron product. So permeability is, in the another language, the permeability is the ratio of the magnetic flux density by the electric field intensity. Permeability is basically two types. One is called the absolute permeability, another one is called the relative permeability. What is absolute permeability? The permeability of the air or the vacuum. It is written by mu naught and its value is 1 by 4 pi into 10 to the power minus 7. What is the value of the relative permeability? The permeability of any medium with respect to the air, and we can write by mu r. So what is relative permeability? Relative permeability means the amount of permeability with respect to iron or any other medium. And what is the total permeability? So permeability can be written as mu naught into mu r. If we tell the mu r for any iron solenoid is 200, so what does it mean? It is the mu naught into mu 0. What is this? This is basically mu naught into mu 0. Then explain the intensity of magnetization. So what is this? When a magnetic substance is placed in a magnetic field, it will experience a magnetic momentum. The magnetic momentum per unit volume of the substance is known as the intensity of magnetization. If two poles of the equal magnitude If two poles of the equal magnitudes but opposite in direction, one is north pole and one is the south pole, are connected by a axis by a distance d, both will feel some torque or some momentum, and the magnetic momentum per unit volume is known as the intensity of magnetization. Next, classify the different types of magnetic material. So as we know, the magnetic material is basically two types. One is called three types. So one is ferromagnetic material. The relative permittivity is very high. It is greater than 1. If it is very high, we will call it ferromagnetic material. If it is a little magnetic property is there, we will call it the paramagnetic. Another term is there which is called the paramagnetic. So paramagnetic means the mu r is greater than 1 but it is not very big. But for the ferromagnetic, the mu r value is very big. So ferromagnetism is the basic mechanism by which certain material from permanent magnet like the iron, it forms a permanent magnet or are attracted to the magnets. If we bring anything near to it, it will attracted by the magnet. What is the example? Iron, cobalt, nickel and any other some alloys. What is diamagnetic? Diamagnetic material mu r is less than 1. Diamagnetic materials are repelled by the magnetic field. An applied magnetic field creates an induced magnetic field in them in the opposite direction, causing a repulsive force. So diamagnetic materials are in the mu r is equal less than 1. They are repelled by the magnetic field. What are the example? Copper, gold, antimony, silver, lead, hydrogen. These are the diamagnetic. Mu r is less than 1 but not 0. And what is the third one? Third one is the non-magnetic. Non-magnetic means mu r equals to 0 and this not means the relative permeability is 0 and they are not attracted by any types of magnet. So it is there are the different types like wood, plastic, cloth. These are the non-magnetic material. So magnetic material is basically three types: ferromagnetic, diamagnetic and non-magnetic. Ferromagnetic mu r is greater than 1. It has some attractive force. diamagnetic mu r is less than 1, it means it has some repulsive force and it is the mu r equals to 0. There is no attractive force. And paramagnetic material means which has the magnetism property, like paramagnetic mu r is greater than 1, but it is very weak. Next important topic is the state and explain the importance of Biosubards Law. So as I told in the slide 2, the electromagnetism is based on the two law. One is called the Biosubards Law, another one is called the Ampere's orbital law. So first one is the Biosubards Law. The magnetic field in due to the current element I dl, if this is a current element I and this is a small length dl, if we are assuming the small length dl, the field intensity dh at a point P we can calculate using the Biosubards law. So according to the Biosubards law, dH is directly proportional to I into dl, and dH is also proportional to the sine theta, the angle between the current element and the joining length here. So this is the theta angle. So here we will, as dl is a differential length, we will think this is a point. So we will get a sine theta angle. And what is dh? dh is inversely proportional to the distance r. So this is the three things on which the Biosubards law depends. dH is directly proportional to ideal, dH is directly proportional to sine theta, dH is inversely proportional to I r 1 by r square. If we combine these three, we can get dH is directly proportional to I dl sine theta by r square. So if we write it in the equal proportionality constant, we can write dH is equal to I dl sine theta by 4 pi r square, where 1 by 4 pi is equal to the proportionality constant. So what is B? B is equal to, we know that what is H? H is equal to integration in a closed path I dl sine theta by 4 pi r square. And H and B relation is H is equal to B is equal to mu into H. So B is equal to mu integration of I dl sine theta by 4 pi r square. Now, if we write it in the vector form, what will happen? We know that the A cross B is equal to AB sine theta. So, here we are getting I dl sine theta. I B dl and this is sine theta. So, we can write it by I cross dl. So, the Biosubards law can also be written as dH is equal to I cross dl by 4 pi r square. As I is not actually a scalar quantity, we can write that I constant dl cross AR. The magnitude of AR is always 1, and so we can write I dl cross AR 4 pi r square, and this is the vector form of the Biosubards law. dH is equal to I dl cross AR 4 pi r square, where AR is the unit vector and its magnitude is 1. Next is the superconductor. What is superconductor? Superconductor is a material that offers no resistance to flow of electron and conducts electricity. Generally, the conductor has the less resistance, but it has some resistance. But the superconductor is a material that offers no resistance to the flow of electron and conducts electricity. The superconductivity phenomena was discovered in the year of 1911 by the Dutch scientist or Dutch physicist once. So it is the superconductors are the special type of metallic alloy when it is cooled up under a certain threshold temperature, it loses the electrical resistance property and become superconductors. So superconductors are elements or metallic alloy. When cooled below a certain threshold temperature, it loses its electrical resistance property. What is the example of the superconductors? Superconductors are niobium, cuprate, magnesium diboride. So these are the superconductor. Generally, the resistance is very less, and when it is cooled below a certain threshold value, it loses its resistance property totally. Okay. Next, write the expression for magnetic field intensity due to the infinite state conductor. Now think, this is an infinite state conductor and the length is L. The amount of current flowing through is I. We have to calculate the intensity P at the distance is R. So according to as we discussed earlier, the field intensity is equal to I dl cross AR. AR is the unit vector by 4 pi r square. Or we can see from here dl, this is the z direction. So we can write I r dz. If this is r, so it is the r dz into a phi by 4 pi r square. So the direction is then a phi. So if we want to calculate the integration, let's assume z is equal to r tan theta. So what is dz? dz is equal to r sec square theta. So z square is equal to r square tan square theta. Now the conductor is infinitely long conductor. So when z is positive infinity, the theta value will be, what is theta? Theta is equal to tan inverse z by r. So tan inverse infinity means the theta is equal to pi by 2. And similarly in the negative direction also, if z is equal to minus infinity, theta is equal to plus pi by 2. So if we keep the integration in between plus pi by 2 to minus pi by 2, we will get, after integration, h is equal to I by 2 pi r, and the direction is a phi, the direction in the angle. So the magnetic field intensity H for a long infinite conductor is H is equal to I by 2 pi r. So this is the expression. Next, state the ampere circuital law. Ampere circuital law is the another important circuital law. As we discussed in the second slide, the two main law which dominates the magnetostatics, one is Biosubards law, we have discussed just now. Another one is the ampere circuital law. So if there is a current carrying conductor, it will create a magnetic field around it. And what is the intensity of the magnetic field? The Ampere circuital law states that the line integral of the magnetic field intensity around any closed path is equal to the total current enclosed by the path. So what is this? Ampere circuital law states that line integral or the normal integral of the magnetic field intensity H integration dl is equal to the amount of the current around any closed path is equal to the total current enclosed in the path. If the current flowing is I, then H comma dl is equal to I. Then write the application of Ampere circuital law. The Ampere circuital law can be used anywhere where the magnetic field is presented. So for the electrical machines like motors, generators, transformers, we can use the Ampere circuital law. Ampere circuital law work with the principles related to the Ampere circuital. All of this work with the principle of Ampere circuital law. That is, the magnetic field intensity H into dl is equal to I, where I is the, if we place a current carrying conductor, the H dot dl is equal to the current flows in the closed path. So we can use it in any type of solenoid, any type of toroid, or any type of single line circular path. All types of application we can go for the Ampere circuital law. Okay. Next important question is the extract the expression for Maxwell's second equations. So Maxwell's first equation is related to the Gauss law. This is the Maxwell's second equation, which is related to the electromagnetism. So from the Gauss law, we can write, if we think about the Gauss law of the magnetic field, we can write the magnetic flux in a given surface is the surface integral of the magnetic flux density. Similar like the electric Gauss law for the electric field, that the magnetic flux, if it is a surface, then the magnetic flux in the given surface is the surface integral of the magnetic flux intensity. So we can write psi, or we can also write it phi, is equal to integration of B dot ds. What is B? B is equal to the number or the flux density, and ds is the cross-sectional area of this path. But in the case of the magnetic flux density in any closed path, total amount of lines of force is always 0. So as the lines of force is 0 means flux is 0, and flux density in the closed surface is always 0. So we can write that the B dot ds equals to 0. So B dot ds is equal to 0. Or if we use the Stokes theorem, if we want to change the so this is the integral form of the B dot ds is equal to 0 is the integral form of Maxwell's second law. Now, if we use the Stokes theorem, what will happen? I have already discussed in the previous session that the Stokes theorem is used for changing the surface integration to the volume integration. So, B dot ds is equal to volume integration of grad B dv. So, if we equate the both sides, we can write grad B equals to 0. And this is the point form or derivative form, of the Maxwell's second law. So Maxwell's second law is based on the Gauss law of the magnetic field intensity, and according to this law, the flux will be zero in a magnetic field. So B dot ds is equal to 0. This is the integral form, and the grad dot B equals to 0. This is the point form or derivative form. Next, extract the relation between B, H, I and L. I have discussed this in the many times in the previous all slides. Just I am writing here that the H is equal to, we know, N I by L, where N is equal to number of turns and L is equal to length of the coil. So we can also write that the B, what is the relation between B and H? B is equal to mu into H, where mu is the permeability of the medium. So if we combine these two equations, we can write B is equal to mu N I by L. So this is the relation between the B, H, I and L. B is equal to mu Ni by L. Interpret the expression for magnetic field intensity on the circular path. So we have to calculate the magnetic field intensity when the current carrying path is circular. So we have to calculate the intensity in any point near at the center of the circle. So we can write that from the Biosubards law, we have to calculate the field intensity at the center P of the current carrying conductor. So according to the Biosubards law, we can write dH is equal to IDL sin theta by 4 pi r square AR. So what is the angle? It is this is known that the radius always makes a 90-degree angle with the arc of a circle. So theta is always 90 degree. IDL theta is 90 degree means sine 90 degree by 4 pi r square. So DH is equal to IDL sine 90 is equal to 1 is equal to by 4 pi r square. So H is equal to integration of IDL by 4 r square, or H is equal to I integration of DL by 4 pi r square. What is DL? DL is the total length of this path. So what is the total length for a circle? For a circle, the total length is the perimeter of the circle, and the perimeter is 2 pi r. So we can write I into 2 pi r divided by 4 pi r square. So pi cancel out, we got H is equal to I by 2r, and this is only for the one path. If the circular path is a solenoid or there are n number of turns, then H is equal to Ni by 2r. Next, interpret the Maxwell's third equation. Actually, I wrote Maxwell's equation. It should be Maxwell's third equation. So, from the ampere circuital law, we came to know that the integration of H dl is equal to I. Again, from the normal equation, we know integration of J ds is equal to I. What is J? J is equal to current density di by ds. So di into J into ds. ds is the surface area. So I is equal to J integration of J dot ds. So H dot dl is equal to J dot ds. Now, as this is dl and this is ds, we have to apply the Stokes theorem to equate the both sides. So H dot dl is equal to grad cross H ds. So if we compare these two equations, we get grad cross H ds is equal to J ds. So we can write grad cross H is equal to Z. Grad means curl of H, and this is the point form of Maxwell's third equation. This equation is the integration form of Maxwell's third equation. So there are two equations. One is the integration form, another one is the point form. Next, a current, this is a small problem is also there. A current carrying conductor is 1 ampere current is flowing in a circular coil of the radius of 10 centimeter and 20 turns. Calculate the intensity of the magnetic field at a distance of 10 centimeter of the coil and the center. So first we will calculate at the center only. So how to calculate the magnetic field at the center? Magnetic field is if it is 10 ampere current is flowing and this is a current carrying conductor path, we just deduce the formula H is equal to I by 2R. R is the radius and radius value is given as the 10 centimeter. If anything is in the centimeter, we have to convert it into the meter unit. So 10 centimeter is equal to 0.1 meter. So 0, and what is the amount of current flowing? The current flowing is 1 ampere. So we can write H is equal to I by 2R. So from the circular coils N turn, H is equal to Ni by 2R, where N is equal to number of turns and there are 20 turns are there. 1 is the amount of current flowing through this. So 20 into 1 by 2 into 0.1 and the unit is 100 ampere turn per meter. So this is already done, the interpret of Maxwell's equation. So what we have discussed today? We have discussed the small revision. What we have discussed? We have discussed what is magnetostatics, what is the difference between the electrostatics and magnetostatics, then what is the important law for electrostatics and magnetostatics, what is permeability, what is intensity, what is susceptibility, what is the magnetic flux density. Then we discussed about the difference, the types of the magnetic material like ferromagnetic, diamagnetic and non-magnetic according to the permeability of the medium. Then we have discussed about the Biosubards Law, one application of Biosubards Law, Ampere circuital law, the Maxwell's second equations and Maxwell's third equation. So this is up to today's class and thank you.
Like, share and subscribe. Hit the bell icon for more updates.